Heidi. Sorry, Heidi.
Okay, hello. So as stated, my name is Heidi Chavez, and I worked in Dr. Luis Santiago's lab in the botany and plant department. And the title of my completed research is Leaf Water Potential is Related to Spectral Reflectance in the 5 Native California shrimp species. So California has often suffered from extreme droughts that can last up to months and even years. And with climate change impact becoming even more extreme in California, this is something we need to look at. And so by investigating how drought will affect plants, researchers can help determine how different plant species will respond to drought stress in future ecosystems as the droughts in California get more extreme. So some key plant hydraulic terms that I'll be using in this presentation are plant water potential, which is defined as the plant water status in units of pressure, which is megapascals. And then turgor loss point, which is the water potential at which cells lose turgor and begin to wilt. And then we have water band, which is the ratio of spectral reflectance of wavelengths at 970 and 900 nanometers. So there are many techniques we could use to measure plant water status. And one of the ones I used was a pressure chamber, which can be seen at the top right and bottom pictures. So using these pressure chambers, we often have to collect the leaves and take them back to the lab to take repeated measurements to get a good look at the water status of a plant throughout the day. And this can be very challenging on small shrubs, given that they might have limited amount of leaves. And it would just cause lots of damage to the plant. So an alternative method we could use is the mini list spectrometer, which is shown at the top left. As seen, we could just take it outside and put it up to a leaf to take in any water band measurements without having to cut the leaf and take it back to the lab. It's a much faster way at getting measurements. So 2 research questions we wanted to answer in this completed research is their relationship between water band and the leaf water potential of the 5 California and chaparral and coastal sage-grouse species we had chosen. And if there's a relationship, what did we notice? Our second question is if we observed any differences or similarities between the species in their relationship between water band and relative water content. So for methods and data collection, what we did is early in the morning, we went up to the UCR Botanic Gardens and we had chosen 5 native species from California. And these 5 native species were Salvia mellifera, Salvia lucifera, Ceanothus tomentis, Encilia farinosa, and Agronium facilitatum. So we picked about 3 to 4 leaves and put them immediately into plastic bags and sealed them up in order to halt evaporation of any water from the leaves as we took them back to the lab. And once we had all the species and got back to the lab, we did 8 rounds of measurements throughout the day. And these rounds consisted of 3 types of measurements. So our first step was taking in the water potential using the pressure chamber, which I had mentioned earlier, and it's shown above here again. And that followed by that, we would take the fresh water mass using a balance. And then we would take the water band measurements using the mini leaf spectrometer. So at the end of each round consisting of these measurements, we would then take the bags that had the leaves and put them onto a flat surface. And we would open them and let them dry for a certain time interval. So at the start of our first round, we would let it dry for a minute, and that time interval slowly increased as we went each round. And so at the end of our 8th and final round, the drying time interval was an hour. And once we ended that 1 hour of drying time, we placed the leaves into an envelope, and that was put into a drying oven that was set at 60 degrees Celsius. And we let it dry for 3 days. And then from there, we took measurements of the dry mass of the leaf, and we could use that to calculate the relative water content. So using those measurements that we got, we could use the measurements of water potential and also the amount of water, the volume of water in a leaf to be able to create pressure volume curves for each species that we had. And so using these pressure volume curves, we can see when the species will reach turgor loss point, which is when cells lose turgor and start to wilt. So the pressure volume curve we have here is for Ceanothus, and this is its measurements throughout the 8 rounds we did in one day. So it starts very more hydrated and starts to get dehydrated throughout the day. And by looking at the data on here, we were able to determine that Ceanothus reaches turgor loss at the 4th data point. So this is when its cells start to lose turgor and it starts to wilt. So based on these pressure volume curves, we were able to create an average turgor loss data table, which showed where each species typically reached turgor loss. So Encilia farinosa had the least negative turgor loss at -1.6, and then Engronium had its average turgor loss at -3.7. So one of the relationships we wanted to explore was the relationship of water potential and water ban. And by looking at all the trend lines of all 5 species, we were able to see that there is a relationship. So looking at that data, we were able to see for all 5 species that as water potential decreased, the water ban would also decrease. So Eronium, the data in green, had the most negative water potential, meaning it was the most dehydrated of all species. And then we have Encilia, data in blue, who had the least negative water potential. It was more hydrated compared to Agronium. So in this graph, the water potential values are positive. So when I say that Eronium had the most negative water potential, that would just correlate to the most positive values, and Encilia, who had the least negative values, would just be the least positive values on this graph. It's just the way we had to graph it, but water potential is measured in negatives. And we can see that Eronia was the most dehydrated and Encilia was the most hydrated out of all the species. So the next relationship that we wanted to look at was at the relationship between water ban and relative water content. And so by looking at 3 specific species here, Agronium, Ceanothus, and Encilia, we see that their trend line have the same pattern, that being that as relative water content decreases, their water ban would also decrease. And so Agronium, data in green here, had the lowest relative water content values and water ban. And Encilia, the one in blue, had the highest relative water content and water ban values. So it wasn't losing as much water compared to Agronium and Ceanothus, who did have lower amount of water in their leaf. And so also we did have 2 salvia species on this graph, Salvia mellifera and Salvia lucifera. However, there was like some type of error in measurements that is unknown, given that the trend line doesn't follow the same pattern and the data splits, but it's just an unknown error given that we did multiple measurements in different weeks. So the question we wanted to answer for this completed research was if there was a relationship between water potential and water ban. And we did confirm that there is a relationship. As water potential decreases, water ban would also decrease. And so we did see that the values, they followed the same pattern, but the values across all 5 species were not uniform. It differed despite 4 of them being coastal sage scrubs and 1 of them being chaparral. So by looking at the average turgor loss table, we can also see that despite 4 of them being coastal sage scrubs, those being Encilia, salvia species, and Agronium, they also differ in that. And so despite being from the same biome, we could determine that it was most likely due to different plant characteristics, such as like Encilia, who is shown here at the bottom left, who has a much bigger leaf compared to Agronium on the right, who has these tiny leaves. So despite being both coastal sage scrub species, they didn't have similar values. And so also by looking at the average turgor loss, we can note that Ceanothus and Agronium were around the -3 and -3.7 values. And so it differed greatly compared to the other 3 coastal sage scrub species, and based off this, we were able to determine that Agronium was the most drought resistant out of all the species and out of all the coastal sage scrub species, meaning that it could maintain turgor and continue its metabolism even during low water potential values. And so our second question for this research was also observing if there were any differences or similarities in the relative water content and water band values. And so once again, Agronium had the lowest values in relative water content and water band measurements out of all coastal sage scrub species, and also out of all the entire species that we measured. And so alongside Ceanothus, a chaparral species, they were the most drought resistant, being that they were able to withstand low water amounts in their leaf compared to our other coastal sage scrub species who managed to stay more hydrated compared to Agronium and Ceanothus. And so we were able to determine that water potential is a major indicator of water stress, and together with water band, we could use it to determine how a plant will tolerate or how it will respond to drought conditions. However, we were able to see that despite some of the species being from the same biome, the values aren't uniform, so it will differ per the different species that we investigate. And so in order to be using water band as a reliable tool to measure water potential, what researchers could do is try to take in many more measurements for other species and also use other variables to strengthen the relationship, such as the leaf thickness or the specific area of the leaf to strengthen that relationship. And so that is the end of my presentation. Thank you so much.
Thank you very much, Heidi. Are there any questions from the audience for Heidi?